Yes, today we're going to do sections 3 and 4, talking about ionic bonding and ionic compounds, and then we're going to get into metallic bonding, but specifically with ionic bonding, we're going to compare molecular compounds, which we talked about last lesson, to ionic compounds. We're going to talk about how they're arranged in crystals, look at lattice energy, and talk about how the ionic and molecular compounds compare to one another, and then we're going to wrap it up with polyatomic ions. So ionic compounds, how do we define them? They are most of the rocks and minerals that we see in Earth are going to be ionic compounds. Table salt is really the most common crystal we can think of that we probably see on a day-to-day basis. And if you look at it closely, it is going to have a cubic-like structure. So you see some salt crystals here. If you look at them under a microscope, you'll see them forming these nice symmetric cubes, and we'll talk about that why in terms of its structure. So, specifically with table salt, it's a nice one to look at because we know that sodium on the periodic table wants to lose an electron to become like neon and thus gain a positive charge. And we know that chlorine wants to gain an electron to be like argon and thus gets a -1 charge. Because they have the same charge, sodium wants to lose an electron, chlorine wants to gain an electron. Those charges are balanced out. But note that that's not always the case. Sometimes atoms want to give up 2 electrons or gain 2 electrons. And you're not always going to have this nice 1-to-1 ratio that you do with table salt, sodium chloride. So the definition of an ionic compound, again, is just a compound that's composed of positive and negative ions so that they're combined in a way that their charges are equal. Again, most ionic compounds are crystalline solids, and a crystal is just a 3-dimensional network of positive and negative ions mutually attracted to one another. So unlike a molecular compound, we're building those in the lab, and we can make a little molecule. You can't really make an individual unit of a crystal. I mean, we can build crystals. We even can grow crystals in the lab, but they're more of a network where they just keep building off of one another. So you see here, we've got this network of positive sodium ions and negative chloride ions, making this crystal structure as it repeats and repeats and repeats. It doesn't always have to be a cube, by the way. We're going to see there are different ways that those structures can repeat. But I just said that we don't have a simple molecule like we do with covalent compounds. However, we do have the simplest ratio. So as you can see in the salt, we have a 1-to-1 ratio. So we call that a formula unit. If I just take the smallest unit of this brick of salt, that's what we call a formula unit. And that allows us to say that salt has a formula of NaCl because it's a 1-to-1 ratio. So here's just to remind you, ionic bonds, we see that structure that where electrons are transferred from one atom to another. You have a cation and an anion all formed together in that structure. Whereas covalent bonding, we are sharing electrons between pairs of atoms, and we can see that in the case of an individual molecule rather than a network of atoms. So remember, we can do Lewis dot diagrams with ions as well. Sodium has 1 valence electron. Chlorine has 7 valence electrons. So alkali metals like sodium will always easily lose 1 electron to make that cation. And then on the other hand, halogens like chlorine are always going to easily gain an electron. So it's a nice transaction. The chlorine essentially takes the electron from the sodium. Sodium becomes a positive cation, and chlorine becomes a negative anion. Notice the name change. The anion tends to change its name from chlorine to chloride. Like fluorine would become fluoride. Oxygen would become oxide. Negative anions tend to change their name in that respect. So for ions, the best arrangement that they can make is going to be a crystal lattice, and we have these attractive forces existing between oppositely charged ions and repulsive forces between the like-charged ions. And the combination of these two factors is what decides how far apart the ions are and also the patterns that they're going to make. So we see the cubic structure of NaCl, but there's also other types of structures like the cesium chloride lattice you see there. Instead of one atom being surrounded on 6 sides, now we have the cesium cation being surrounded by 8 chloride ions. So there is different numbers that the ions can be surrounded by to form those crystal structures. So again, these ions are being held together by very, very strong electrostatic forces. Not as strong for covalent compounds. The covalent compounds have much weaker forces holding them together. So that's one main difference between molecular or covalent compounds versus ionic compounds, is the bonds in ionic compounds are much, much stronger. And that leads to some properties we're going to see in lab. Molecular compounds have very weak forces, so they melt at lower temperatures. In fact, we're going to do a lab where you heat up some different substances that look the same, but you're going to see that some substances melt almost instantly when you put the heat to them, whereas other substances might not melt at all with the Bunsen burner. So ionic compounds would be an example of that. Ionic compounds have very high melting points. They're hard, but they're also brittle, which means they shatter instead of, if you think of sugar, you put sugar in the blender, you get powdered sugar, right? Because it turns into a dust. Whereas salt doesn't really turn into a dust. You just get smaller and smaller crystals if you look at them closely. So the ionic compounds will be brittle. They don't turn into like a powder. And they aren't electrical conductors in the solid state. However, they will conduct electricity if they are dissolved or if they're melted. Speaking of melting, it would take a lot of energy to melt ionic compounds. You see 3 ionic compounds at the top. Melting points are in the hundreds and thousands. Same with the boiling points, over 1,000. Whereas the 5 covalent bonds in the bottom, some of their melting points are in the negatives. Even the boiling points are in the negatives. Methane is what we use in lab for our Bunsen burners. When you open the gas valve, methane will come out. And you know it's gas has such a low boiling point. It boils at negative 164 degrees Celsius. You'd have to cool down the room quite significantly to get liquid methane. So this, again, sort of alludes to the lab we're going to do with ionic versus covalent compounds. How can I tell whether something is ionic or covalent? Here are some tests I can use. First of all, let's just examine it. all ionic compounds are solid at room temperature. So if it's a liquid or a gas, then it's immediately covalent. It's not ionic. However, if it's a solid, it could be ionic, but like sugar, it could be covalent. We just have to use some other clues to figure that out. We can tap the substance gently. We can see if it's brittle or if it crumbles into a powder, like I was saying with the. You don't have powdered salt, but you do have powdered sugar. If we heat it up, and its ionic compounds are generally going to have a high melting and boiling point. Also, we can look at conductivity. If it does melt, does it conduct electricity? It also will conduct if we dissolve it. So we can dissolve that substance in water and use a conductivity apparatus to see if it conducts in water as well. Salt does make water a strong conductor, but again, this alone can't determine anything because even sugar will allow some electrical movement when we test it. So all these things together sort of give us the clue of whether something's ionic or covalent. Now, one last thing I want to talk about with ionic bonds is these things called polyatomic ions. And this can confuse some people sometimes because we're looking at an overall ion that's made of different atoms inside of it. So the atoms inside have covalent bonds with each other, but all together they make an ion. So a common example of that would be NH4, which is called ammonium, the ammonium ion. Notice it has a positive charge. So if I were to just look at an N with 4 H's, how many valence electrons does N have? Well, it has 7 total, and then 5 of them are going to be valence, because the one has 2 is an inner shell, and then all the hydrogens are going to have 1, right? So naturally, as just NH4, you're not going to see NH4, right? You could see NH3, but NH4, I don't have enough places to put all the H's because I have that pair of electrons with nitrogen. But if nitrogen just so happened to lose an electron, then it would work, right? Then I could put a hydrogen on each side. So what we want to do, let's give nitrogen its electron back for a second. Let's count the total number of electrons. There's 5, 6, 7, 8, 9 valence electrons. If this thing has a positive 1 charge, what would you expect that to do to the number of valence electrons? Yeah, go down to, now we only have 8 valence electrons, probably removing this one. But we can draw it using our method, put N8N with 4 H's around it. And look at that. 8 valence electrons, 4 bonds, 2 electrons each. Matches up perfectly for us. The only thing is we just want to make sure we put brackets around this thing to show that it has a positive 1 charge. And that's an example of a polyatomic ion. So that could combine with another, with a negative, an anion, and it could make an ionic compound. But notice there's covalent bonds within the ion, even though we call this whole structure a polyatomic ion. Yeah. Yeah, and there's actually, I think there's an example on this slide here, 2 slides up. You see there's a positive one that we just looked at, the ammonium ion. That's a good question, because then we have the nitrate ion with a negative 1 charge, and the sulfate ion with a negative 2 charge. And it kind of makes sense if you look at it, because sulfur has 6 electrons, and so does each oxygen. So if I have all 5 atoms have 6 valence electrons, that would be 30 valence electrons. However, because that alone with the 30 valence electrons, that structure would not hold. But because I'm gaining 2 electrons, that puts me up to 32 valence electrons. And if I count these, I've got the 4 bonds in the middle, 1, 2, 3, 4, so 2, 4, 6, 8. And then each oxygen has an octet, so 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we can see that charge is necessary for that structure to work. If I didn't have the charge, there would be no SO4. But to answer your question, yes, there can be negatives. But does that make sense? How they can be built based on how many electrons are missing or gained? Same with nitrate. You just wouldn't have. Notice we had to have a double bond for that to work with the 1 oxygen. And this is actually a resonance structure because it doesn't matter which of those 3 oxygens has the double bond, but one of them would have to have it. So that's really all I have to say for ionic bonding. Any other questions on that before we go to metallic? So metallic bonding is sort of the third type we're going to look at. With covalent bonding, we had sharing of electrons. With ionic bonding, we had a transaction where electrons were either given or taken away. With metallic bonding, we see that the electrons aren't even really hitched to any particular atom. Electrons are just sort of free to flow through all these nuclei that are bonded together. In metals, we've talked about metals before. They have good conductivity. That's why when you touch cold things, it steals the heat from your body a lot more efficiently than if you touch. I guess I meant to say why cold things are typically metal, because those metals are taking the heat from your body, from your hand. Malleability, remember, it can be flattened into a sheet. Ductility means it can be drawn into a wire. And they tend to be shiny when light reflects off of them. So I already defined malleability and ductility. We've talked about those 2 terms, but they are in your notes. And here are the 3 bonds again. Covalent, sharing. Ionic, give and take. Metallic, we have the electrons freely flowing through all these different nuclei. So all these different orbitals are allowing those electrons to flow freely. And what we call that, because the electrons are flowing freely, kind of like a body of water almost, we call it the sea of electrons, because there's that crystal lattice of metal atoms, and they're basically sharing all the electrons, but unlike a covalent bond, these electrons are delocalized, meaning that they're free to roam around any of the orbitals, because all those orbitals overlap in that structure. And you can see it. Normally I would have this animated, but you can kind of imagine those electrons freely flowing among the positively charged nuclei. So this is why metals are such good conductors, because we need electrons to get from point A to point B to make electricity flow, to power things. So those metals allow for that to happen quite easily. So just to see if you're paying attention here, we've got an unknown substance. It's going to be one of these 3 types. It's good electrical conductor in the solid state, and it's malleable. Which type of bonding do you think that would represent? Ionic, covalent, or metallic? Yeah, I would agree that it's metallic. Why is it metallic and not ionic? Because it is in the solid state. What makes you think it's metallic? Yeah, it's got malleability there. And it's also an excellent electrical conductor. Not that ionic bonds are, but they either have to be dissolved or melted, usually, to conduct electricity. Good stuff. We'll talk about molecular geometry next time.